Hey guys, that last section, this is lesson 5, sets of numbers, subsets of the set of real numbers. And you've likely seen this before, but it's so important that you know the symbols that I'm going to do it again. And so you know, this is how I used to start a pre-calculus class at another college prep school out here in the West. So we were just looking at numbers that were not real, imaginary numbers and complex numbers. These are numbers that you cannot put on the number line, that we will have a different way of graphing them that you'll see in pre-calculus. So we're going to look at sets of the real numbers, numbers that can be placed on the number line. Now, the set of real numbers is universally important. There's actually 3 symbols. Check it out. 3 symbols that symbolize the set of real numbers. And if you know that there's these 3 symbols, you know it's going to be important. So if you ever see an R or a double barred R or a big script R that may be italics or not, they're talking about real numbers. It's kind of that big a deal. So we're going to split this up into subsets. And it's going to be important for you to remember and know what each of these are. So I'm not sure you can see this well enough, so I'm going to pause this and darken this. But if you've already printed out this PowerPoint, you have this written or this table drawn. If you're taking notes, take a second now to fill this table out. Actually, not fill this table out, just to copy over what the headings are. So the headings are the set of numbers. I'll list the numbers if we can, the name of that set, the symbol used, and then new property. That new property will make sense after we filled in most of the tables, so we're going to leave that blank for a little bit. The first set of numbers was the set of numbers you learned watching Sesame Street. And if watching Sesame Street, you may have heard the Count Dracula, or he wasn't Count Dracula, he was just the Count. He was the Count and he would count for you. And he would count by starting with 1 and moving to 2, 3, and so forth. This is known as the set of counting numbers. There's another name for the set of counting numbers, and that's the set of natural numbers. And that's important to know because the symbol for the counting numbers, for the natural numbers, is an N and a double barred N at that. So on the left-hand side, there would be a double bar over here. The next set of numbers, I'm going to close off my braces there. And this is set notations. These little squigglies tell me that I'm talking about a set of numbers. So on the second, I'm going to include now a 0 in that set. 1, 2, 3, and so forth. And these are the set of whole numbers. Whole numbers. And because mathematicians are very creative, the symbol is a W with a bar on it. The next set of numbers we're going to include, so you can see we're including a little bit more each time. The next set of numbers will be -3, -2, -1, all the whole numbers and their additive inverses, 0, 1, 2, and so forth. And so these are called integers. Integers. And the symbol for integers is, what do you think? It's a Z. A double-barred Z. And you're wondering where that came from? It came from the German, and I always mispronounce it. Our German exchange students say, no, Miss Mariner, it's, and they pronounce it correctly. It's Zahl. I'm trying hard. Zahl. So spelled Z-A-H-L, and it's one of the many numbers in, or many words in German that mean number. Okay, Zahl. The next set of numbers, actually, this next set, I'm going to pair them up together. We're going to look at the rational numbers and the irrational numbers as a pair. Hang on. Rational, irrational numbers. And the irrational numbers, the symbol is just an IRR. The rational number symbol is a Q for quotient. That was a little easier, quotient, at least it's something in our own language. And a rational number is the first number here in this list that we cannot list by using what's known as the roster method. We can't just list them and make a pattern of it. We're going to say rational numbers are numbers that can be expressed as A over B such that b is not equal to 0. We don't have Chuck Norris in the room, so he can't help us deal with explosions that would happen when there's 0 in the denominator. We also have to have a and b are integers. So it's possible to express the number as an a over b, where a and b are both integers. So I'm going to use the symbol b comma a. B and a, actually I put a semicolon there, b and a are members of, that symbol is a members of the set of integers. So that means a and b have got to be integers. You can't have a square root there, that doesn't make them rational. Irrational numbers are numbers you can't express as a over b. Where a and b are integers and b is not equal to 0. So I do want to spend a little bit of time talking about the irrational numbers, but let's actually continue to fill out this chart. And if I take all the rational numbers, well, think about that. All the integers kind of fall in the set of rational numbers, don't they? Because even if it's like a -3, you could say -3 over 1. All the whole numbers are also integers and they're rational. All the counting numbers are, you can see we've got that the rational numbers are composed of integers, whole numbers, counting numbers, and then some. Okay, but if I combine the irrational and the rational numbers, I get a complete set of numbers on the number line. I get the set of real numbers, and I'm going to use a capital R. That's the set of real numbers. And we have added completeness. We have every number in the number line. We've taken the rational and the irrational together, and they make up the set of real numbers. So before I go into more details about irrational numbers, let's actually look at what that new property means. So when I moved from counting numbers to whole numbers, we included a 0. A 0 is the additive identity. So now I have the additive identity. Before that, I didn't have that property. I couldn't have done this. I do have the multiplicative identity here. Multiplicative identity here, that's in I lost something. Multiplicative identity there. But in the counting numbers, the natural numbers, I don't have an additive identity. When I moved from whole numbers to integers, when I included those negative numbers, I now have an additive inverse. Remember we talked about that in the little inverse section earlier, about halfway through the trimester. So now when I move to rational numbers, a over b, I now have things like 1/5. I now have a multiplicative inverse. And when I put the irrational and the rational numbers together, I get the set of real numbers. The property we talk about having there is a property of completeness. We have completely filled in the number line, that if I were to combine the rational and irrational, I have every point on the number line. And this is defined as any number that can be placed on the number line. Okay, and that's what a real number is. So let's take a second to look at some examples of irrational numbers so that we know the difference between irrational and rational numbers. So let's look at some examples of rational versus irrational, because that seems to be where people get kind of a little confused. Rational numbers are any natural number, whole number, integers. Those are all considered rational. It's a number that can be expressed as a over b, where b is not equal to 0 and a and b are both members of the set of integers. Terminating decimals, and let's explain why. If you have, 0.7, that's equal to 7/10. If you have 0.35, that's equal to 35 over 100. So if the decimal is terminating means it ends, then you can express that as a fraction, put it over 10 or 100, or if you have a third digit over 1,000, etc. If you have a repeating decimal, that is a number that can be expressed as the ratio of two integers, and I'll show you how and why in a second. I need a new lead in my pencil, so hang on a second. So hey, let me ask you one more thing. I got to remove this blue thing. What if I have something like this, square root of 16? Is that rational or irrational? You know what? Always simplify. Square root of 16 is equal to 4, so therefore it's definitely in the rational component. Be really careful about that. Sometimes on tests and quizzes, your teacher tries to trick you and put the square root of 25 and ask you if it's rational. And of course it's rational because you can simplify it. So let's actually go back and take, you may know that as 1/3, 0.3 repeating, 0.33333. Then you can test that out. Take 1 divided by 3 in your calculator. But let's say you're given the decimal. How would you go about demonstrating that it's rational? So let's start by saying, okay, let's be equal to x. So if I have, and I'm going to write this a little differently, I'm going to say x equals 0.3 repeating, and think about that as 0.33333 going on forever. And then I'll take 10x, I'll put that up here, 10x is equal to, well, if I multiply it by 10, that's going to be 3.3 repeating. Is that okay? And then if I have x, that's 0.3 repeating. And then when I subtract, I'll subtract. So I subtract both sides. We've done that kind of thing before with simultaneous equations. So I'll subtract. I've got 10 minus 1 is 9x. And then I've got 3.3 repeating. I'm going to subtract the whole repeating part of things, and I just have plain old 3. So then I have 9x equals 3. Divide both sides by 9. I have x equals 1/3. How cool is that? So now you've proven that. So let's do this with something else. So 0.4, if I start with, and I had to do this in another color so you can see my notes will look better. Let's say, okay, then 10x, if this is 0.4 repeating, okay, so 10x is going to be 4.4 repeating, and x is 0.4 repeating. When I subtract, that repeating part, the 0.4 repeating, disappears. And I've got 10x equals 4. How cool is this? When I divide, x equals, when I subtract, 10 minus 1 is not 10. 10 minus 1 is 9. So when I divide, I've got 4/9. So 0.4 repeating is equal to 4/9. Test that out in your calculator. Take 4/9 and put it as a decimal, and you'll see it's 0.4444444, and so forth. So some people say, before we go on and do this next one, some people say, well, 0.9 repeating, that's not equal to 1. Do you think you could prove 0.9 repeating is equal to 1? So let's put that down as a task. Prove 0.9 repeating equals 1. Use the strategy we just saw. So when you find, so go ahead, pause the video. See if you can do that on your own, and then I'll do it so you can verify. So if you have 10x equals 9.9 repeating, and just plain old x equals 0.9, are we okay with that? Then I subtract, and I've got 9x equals 9, and then when I divide, I get x equals 1. Oh, how cool. Okay, so let's go back and look at what if it's two numbers that are repeating. So this is my example. I'm going to come over here. I need to leave myself a little more space. So I'm basically looking at 0.32 repeating, and I expressed it as 32323232, and ... so you get the idea. That's in forever. If I multiply by 10, that's not enough. So I'll start by multiplying by 100x is going to be 32.32 repeating. And then x was just plain old 0.32 repeating. So then I have 99x equals 32, and you bet I divide and I get x equals 32 over 99. And this is a demonstration of how any repeating decimal is actually a rational number because you can express it as a ratio of two integers. So some examples of irrational numbers: square root of 2, square root of 5, square root of 3, square root of 11. Non-repeating decimals, and I like to use something like 1.01001001. You get the idea. So this is a pattern. This is a pattern, but it's not a repeating pattern. I can't put this as a ratio of two integers. Non-repeating decimals also include pi, that's a non-terminating, non-repeating decimal. There's a number in your future called